Welcome to this NPTEL course on Advanced Pre-Stressed Concrete Design. We are discussing about the continuous beams and we are moving into the module 2. Here particularly we will talk about the principle of linear transformation and also how to go about designing a continuous beam. Right, what are the expected learning outcomes? After the student goes through this video, he or she should be able to understand the principle of linear transformation and explain about the concordant cable profile, what it is, and discuss the design process of a continuous beam and with an example. Right. So let's first talk about the analysis and design considerations. So this you can see a typical box girder that is being post tensioned, and as you can see in post tensioning, because of the friction, right, and losses are going to be significant, right. Friction losses, we have talked about wobble effect and the curvature effect due to which the friction losses will happen. So typically to reduce this is particularly important for a continuous beam, because you run the cable across multiple spans and there is going to be a cumulative change in the curvature of the cable profile, right. So you see here, this is the duct. I think we run the cable like this, and the cable keep changing its direction depending upon the moment profile that you are going to get, right. So to reduce the friction, typically what we do is a sequential stressing. First, for example, you see here, we look at different sections here. You put the jack and then you stress these cables like this, some of them from one side, then the other cables will be stressed from the other side, right. So then finally, after all these things are done, so when you do this pre-stressing or post-tensioning in a staged manner, then you will have reduction in your friction losses. So that's how you are going to do it. So you do it in multiple stages, right. Now after the post tensioning is done, we also do the grouting. Typically, if it is a bonded system, in India the bonded system is very common, as we have discussed in the types of post tensioning. Then we do the grouting. We inject the grout like this from one end. We also have venting tubes to remove the airlock, and then we see that the entire duct is grouted really well. So we need to make sure that you do this sequential post tensioning to reduce the effect of your friction losses. Now from design point of view also, we should also keep in mind that the location and eccentricity of the tendon after stressing, it has a tendency to either move up or down inside the duct. That will lead to reduction in your available eccentricity. For example, if you look at it at the bottom location, the tendency of the strand in the duct is to move up. So you find that the CG of the strands actually gets shifted. It's not going to be exactly at the center line of the duct. It is going to be somewhat moved up. So there is a reduction in the available eccentricity is going to be taken into account, particularly when you are doing, let's say, 31 tendon size, where you have 31 half-inch strands are there. Then let's say, for example, the sheath diameter you need to have 102 millimeter, and this eccentricity, the correction that what we are saying, 14 millimeter has to be accounted for. So the E cannot be measured with respect to the CG of the duct. You have to subtract this 14 millimeter if you are using a 31 number cable, strand cable, right. So you may see that why it's only 14 mm, it may be not make a difference, but when you have 31 cables which are stressed to a high force, that even a small eccentricity will create a reduction in the pre-stressing moment that what we are applying. The same thing that happens at this top location also. Ideally at the support location, we want eccentricity to be as close as possible to the top fiber. But here it exactly happens in the opposite side. So this is the central line of the tube, but your eccentricity CG is going to be somewhere here. So there is going to be a reduction in your available eccentricity, that we need to take into account support location, right? Now, typically when you do this, for example, you see here, this is a two spans with a single cantilever that you have, and depending upon your the loading that you need to balance, for example, this is W2, W3, W1 is the load that is required for balancing. Then we typically in post tensioning, particularly in slabs, at least we try to balance about 80 to 100% of your dead load effects. Okay, so that means you design pre-stressing in such a way that the dead load effects are almost nullified, and so basically, we have studied about in the equivalent load method, pre-stressing creates a vertical load, right, in opposite to what you're going to get from an external load. So you design the pre-stressing in such a way that the upward load created by pre-stressing is going to balance at least 80 to 100% of your dead load. So that's the concept. So now we can see that if let's say I have to balance W1, so I can choose the eccentricity E1 in such a way that P into E1 should be equal to W1 into L1 square by 2. Similarly, for the span 2 with the length of L2, you can see that the average drape is going to be E1, this is E3, right? This is E3, this is E2 plus E1. So it's going to be E1 plus E3 by 2 plus E2. So E2 is here, right? So this is E2, right? So this is the drape that what we are saying. So this drape is nothing but E1 plus E3 by 2 plus E2. So that is this drape. So that is what we are calculating. That P into the drape should be equal to the total static moment that that particular span is being subjected, which is basically W. In this case, it should be actually W2 into L2 square by 8 for span 2, right? Similarly, for span 3, if you look at it, the drape is going to be E3 by 2 plus E4. So this is your drape. This is equal to this, right? So that is what we are saying. So P into drape should be equal to W3 into L3 square by 8. Okay. So this is the way that you choose. So for example, you select P that is required for balancing certain fraction of your dead load. Let's say that these are the dead load that you want to coming in the each span. So then which P would you take? So ideally we have to take the maximum P, then accordingly you design for that. So you design P that is required from each span design requirement to balance 80 to 100% of dead load. Then you choose the maximum P so that it will be satisfying for all the spans. So that's the idea. So in this way you select your P. Now you see here the profile what we have shown is basically it's going like this. But in practice you cannot have this kind of an profile. That's why we say this is an idealized tendon profile. You cannot have sharp curvature there. So practically, typically what we do is we make sure that there is going to be a reverse parabola whenever there is a curvature change. So that we will see. So this is again for another case. What is the idealized profile for two spans with a point load? So this is again for a continuous systems. If you see here, this particular span L1, I have W1 per meter, and you have a point load W2 that is coming. Okay, this is again L2, right? L2 that is here. So for span 1, what is the total drape? It is basically E2 here, right, and E1 here. So it is going to be E1 plus E2 by 2. So the drape is measured from here to here, right? So I join a straight line from the end to this. So it goes like this, and the drape is measured exactly at the maximum drape that it is possible is E1 plus E2 by 2. So that's what you have. Now what is the load that it is there? W1. So I have to balance the load as W1. If we keep it, P into total drape should be equal to W1 should be equal to P into total drape into 8 by L1 square, or in other words, W1 into L1 square by 8 should be equal to P into drape. So you can calculate W1 as P into total drape into 8 by L1 square. So that's what we have. Similarly, for span 2, which is having a point load. So, you know that for whenever you have point load, the cable profile should have a sharp change like this, right. So, this is the total angle change. Let us say this is an alpha. Then what would be the total drape here? In this case, it is going to be E3 plus E2 by 2. Now, you have point load. So, the total moment is going to be W2 into L2 by 4. This should be equal to P into drape. Okay. So, from here I can calculate, if I want to balance the entire W2, then I choose P and drape in such a way that the entire W2 is getting balanced. So, in this way, for continuous spans, quickly we can calculate from, of course, you have to satisfy the cover requirements, and from fire resistance point of view, from durability point of view, from whatever the maximum cover that it is possible, from there you can back calculate what is the maximum force that is required in each span. Then you choose the maximum force, because it's a continuous system, you have the same cable that is running across all the spans. So, you have to choose the maximum force and then you do the pre-stressing, and then that will satisfy. So, in that process, of course, some spans should not be overstressed also. That also we have to keep it in the mind. So, for example, you see here in this location in the second span, the center of gravity of the concrete and center of gravity of tendon coincides at the end of the member, because we do not need to satisfy or balance any equivalent load moments are not need to be applied. Okay. So, that is why generally typically what we will have, we will try to have the CG of the tendon will be coinciding with the CG of the concrete at the end supports if they are simple and there are no moments are required. Okay, so this is another thing. So, we talked about the idealized condition, but actually we cannot really create that kind of an idealized cable profile with a sharp curvature change, right. So, what we do is we create a reverse parabola like this. So, from here to here. So, there is a minimum S1 dimensions that typically the PT supplier will give you, and we can calculate what should typically this S1, if you look at it, this is close to the support, it changes. So, the S1 is typically about 5% of the span on the left side and 5% of the span on the other side. So, typically that is the thumb rule that typically we use. Okay. And then we choose point of inflection like this, right. So, you get here, and this is your point of inflection. So, when you have such kind of a parabola, reverse parabola, parabola and reverse parabola, what kind of loading that you will have? You will find that wherever you have reverse parabola, the load will be actually acting downward. At wherever you have a parabola, you will have load like this. This is what we want. So, in the span direction, we want most of the locations in the span to be of this shape, so that you create the vertical load due to pre-stress. And if it is a parabolic cable profile, you know how to calculate the vertical force that is required. So, this is the resultant balance. Now, because the reverse parabola is usually concentrated close to the support or maybe just little extending to the support on either side of the support, you will have the load, the W1, that will pretty much it will go to the column. So, we are worried about what is the balancing load that it is happening on the span only. Okay. So, in this way, this is an idealized profile. So, we cannot create a sharp profile. It is very difficult to achieve it in the field. So, typically we provide this parabola and reverse parabola to make sure that the transition is very smooth, and whenever you have reverse parabola, the load is going to be acting downward, and that happens usually close to the support region, right, like what you have here. This is also like this. It's going to be right. Okay, so this is again percentage of the dead load to balance. Again, we have talked about this. So, typically when we say, here is a reverse parabola, right. So, this is also reverse parabola, portion of it, if you take one span. Okay, these are the two inflection points, right. So, this is the load that we can apply, right. So, we need to make sure that choose the P and the drape in such a way that 100% of the dead load is balanced typically. Okay. This is again depending upon your design requirement. For typically for PT slabs, At least we try to balance about 100% of the dead load, right? So now when you can also have a reverse parabola with one inflection point, so only one here like this, so you will have this W1. So again you have to choose your W2 and W3, how much you want to balance. Accordingly you have to choose your the amount of pre-stress and the drape that what you want. Again the drape also you have to satisfy the cover requirements from durability and fire resistance. So we want to put as much as maximum eccentricity as possible, but without violating the concrete cover requirements that are specified by the design codes. So this you have to keep in mind. So now let's discuss about the principle of linear transformation. So Guyon's theorem states that when the profile of the CGS is moved over the interior support of a continuous beam without changing the intrinsic shape of the profile in each individual span, then the profile is said to be linearly transformed. So what does it mean? So basically I am just moving the let's say imagine the cable like a thread. I am just moving it up or down without really changing the intrinsic shape of the cable profile, or in other words the curvature of the cable profile. So if you do that, that means you are only linearly transforming the cable profile, right? So in the linear transformation, again the curvatures of the cable remain constant and the locations of the bends also remain unchanged. So this is the assumption that we are making in this theorem. So you see here the example what we can see here is given here, and we have a cable profile like this, okay. It goes like this, right? Now what we are doing here is we are just moving this over the interior support from here to here, right? And similarly I am just pulling this cable and I am just moving it up like this. Similarly from here I am moving it up here, from here I am moving it up here like this. So I am just pulling the cable up, okay. The intrinsic shape of the cable is not really changed. That means the total curvature in the cable in each span is also not changed, okay. So when we do that, this is what is called as linear transformation of the profile. Now again, linear transformation cannot involve the movement of the CGS at the ends of the beam or at the support of a cantilever. This is, you have to keep it in mind, okay. You are interested only in the interior supports that moving the cable profile. So now why do we do that? We know this is what we are going to study in the next slides. There is something called concordant cable profile. To achieve that concordant cable profile, we typically do this. So now let's look at principle of linear transformation with the 3 examples, okay. And this example, it basically illustrates the variations of primary moments, secondary moments and pre-stressing moments, and there is a thrust line that we talked about even in the last lecture also. How do we get that? Okay. So I am taking case A, it's a 2-span system with a constant eccentricity of the cable like this, okay. So I have this, right, and I am applying some pre-stress. Now what would be the primary moment? We have seen the primary moment is nothing but the pre-stressing force multiplied by the eccentricity, and we plot it assuming that there are no interior support. So this is your primary moment. Now what is secondary moment? Secondary moment will be created by the reaction that are developed in the intermediate supports, which is going to push the beam downward and it is going to create a positive moment. We have seen that. Let's say that I found this reaction using method of superposition or some other methods, and I found this value, and then if I calculate the moments, so this is what I am getting. This is basically your secondary moment, okay. So what we have is your secondary moment, right. So this is your secondary moment. Okay. Now, what is the total moment? So this is what we said in the last lecture. M1, this is M1 prime, and this is M2, which is summation of M1 plus M1 prime. So this is what you get. So you get negative PE at the left support, positive PE by 2 at the mid location, and then I get again next is a negative PE at the right support. So for this, now how do we get the thrust line or the C line? So this is also called a C line, thrust line. How do we get the, because why this is called zero load C line is, at this point of time, we are looking at only the effect of pre-stress, the external loads are not acting, right? So if you do that, you divide everything by negative P, then you get your positive eccentricity here, and then it goes like this, and then comes like this, right? So this is how we get your zero load or compression line, or is it also called as the thrust line, right? This is a thrust line. You get like this, right? So I am just dividing the M2 by negative P, because what we have seen in the last lecture also is that the positive eccentricity should produce negative moment. So if I have to take that, then the negative will be divided by the negative P to get eccentricity. So here it will be positive eccentricity, that's what we have. So everywhere you get this, okay. So this is your zero load compression line or a C line. Now see, this is one example. So now if I change the profile of the cable, let's see what happens, okay. So that's what we said, linear transformation. I am going to look at now what is going to happen if I just take the cable at this position, right. Let's say at this position, and then I am just moving this by up, just linearly moving up, right. So my cable I am going to get like this. So that is what we have here, right. You see here, this is E minus C. So I have just only interior support, I have just pulled it up, okay. So you see here, if I do that, again for this profile, if I start calculating the primary moment and the secondary moment, you get the primary moment as this, again minus P into E, here plus P into E, and here it is minus P into E. Primary moment, you know that it is just the multiplication of the eccentricity with the pre-stressing force. Now again for this profile, let us say that using some method of superposition, I calculate this reaction that is required, because again it is a continuous beam. When you do the pre-stress, the beam will try to move up, and in that process, because you have support, the reaction will be developed, it is going to push the beam downward. So that reaction is this, right. So let us say we find through some method, so we get this, and this is your secondary moment, which is your M1 prime. When you add these M1 and M1 prime, now you will find that the total moment is still minus PE, PE by 2 and minus PE here, which is exactly same thing that we got in the first profile itself. Though the profile for A and B are different, both of them are leading me to the same M2 diagram, right. Now for this cable, when I look at it, again for zero load compression line, now what will happen? So basically you will find that this is going to again come like this, okay. So this is your zero load compression line, right. So it is going to come like this. So everything, so this is your zero load compression. Now you see here, this profile is, if I divide everything by minus P, then you get plus E here, here you get minus E by 2, here it is plus E, right. So by changing the cable profile, what I have done is the M2 diagram does not really change, and the zero compression line is also exactly remaining the same. Here also it is plus E, here also plus E, here also minus E by 2, here also same. So you can see that the thrust line has not really changed if I just linearly transform the cable at the interior support. We can illustrate this by one more example. So you see here, instead of moving the cable to minus E, now I have just transformed only to minus E by 2, half of that. For this also again we can create a primary moment, which is minus P by 2 and minus P here, right. And in this cable profile, if you find, your reaction will work out to be the RB here will work out to be 0. Okay, RB here the reaction. So, there is a cable profile that is actually producing 0 reaction. If there is a 0 reaction, again the secondary moments are also going to be 0. So, here you see M1 prime is 0, there are no secondary moments, no secondary moments. So, you get again, but finally if you look at the moment diagram, here also minus P plus P by 2 minus P. So, in all the 3 cases, though I have linearly transformed the cable profile, my M2 diagram has not really changed. Similarly, my 0 load compression line or a C line or thrust line, that has also not changed, but there is a cable profile that is giving me 0 reactions while I do pre-stress, that leads to 0 secondary moments. So, that means there exists a cable profile where I do not get any secondary moments. So, I can find a concordant cable profile by linearly transforming the cable in such a way that it is going to be a scaled factor of a moment diagram itself. Okay. So, for example, if you see here, what are the cable profile that we have? So, here it is plus E, here it is minus E by 2, here it is plus E. So, this is exactly where the thrust line is actually following the CG of the strand itself. So, that indicates that there are no secondary moments. This is also, if you look at it here. So, these 3 examples illustrates the concept that by using principle of linear transformation, we can find out a concordant cable profile. So, which we will talk about it in the coming slides. Okay. So, in a continuous beam, the profile of the CG of the strand can be linearly transformed without really changing the position of the resultant pressure line, right. So, again for example, if you go back to the previous case, the 0 load, this either this or this or this, all the 3 cases the C line did not really change by linearly transforming the cable profile. So, that is what we are trying to tell here. So, even if I for each interior support, whether I move it like this, move it like this, move it like this, you know, your C line is not really going to change. Okay. So, that is what it is. So, but while you are doing the process, you can choose a profile, a concordant cable profile, in such a way that the pressure line will be coincident with the CG of the profile itself, because again why? In concordant cable profile, M1 prime will be 0. So, that means M2 will be equal to M1 itself, because you are not creating any secondary moments. When I divide the moment diagram divided by the pre-stressing force, you will get exactly the EC will be equal to, let us say, the eccentricity of the profile. EC is the location of your compression line and E is the eccentricity of the strand. So, EC will be equal to E for a cable profile that is concordant. Okay. So, a concordant profile does not produce any reactions at the supports or secondary moments in the spans, right. So, in a concordant cable profile, the upward and downward equivalent loads, they try to balance each other. So, you do not need to have any additional reactions developed at the intermediate supports. Okay. So, this is just see, this is a very I should say theoretical or an idealized condition, but typically in practice we do not really necessary to have concordant cable profile. Most of the time concordant cable profile will not lead to very efficient and effective designs. So, you know, you try to avoid secondary moments, but there is no need for you to avoid secondary moments. You can consider the secondary moments, calculate it appropriately and include them. In fact, we have seen that the secondary moment in fact can help in reducing the demand at the negative moment regions, which are basically support regions. but it may increase the positive moment in the span location. So, we have to account for that, but usually we know that the pre-stressing force will be controlled by the hogging moment requirements at the support regions, which will actually control the amount of pre-stress. So, if there is a beneficial effect of reducing that by the secondary moments, it is going to actually help you with coming up with a more economical and efficient design. Right. So, this is a concordant cable. So, there is a no secondary moment in the spans due to pre-stress. The M2 diagram will coincide with M1 diagram. Right. So, that is what we said. The pressure line due to the pre-stress coincides with the cable profile. The shift of the pressure line due to external loads can be measured from the profile directly. Okay. Or in other words, this is what you see here. Now, let us say this is a loading, that external load that is coming on a continuous beam, and I get this moment diagram. I do some structural analysis either using moment distribution method or some stiffness method, and then you get my moment diagram like this. Now, I take some value. This entire moment diagram if scaled by a constant value, and that if you choose that as a profile, that becomes actually a concordant cable profile. Okay. So, for any loading that is there acting on the beam, you do structural analysis and you get your moment diagram, and then if you scale the moment diagram by some constant value, and that value if you choose that as a profile for your tendon, that profile itself will become your concordant cable profile. Okay. So, that is a theory. So, we can prove that. Okay. So, if you choose that, then we will find that M1 prime will be equal to 0. But in that process, what will happen is you will have, for example, in this location, let us say I am getting this eccentricity here, but actually I can go up to this. So, that will give you more effective design. Similarly, for mid span, I can have this kind of a design. So, actually I can go like this and go, and then I can go like this, and then I can go, and then maybe I can go like this, and then I can go like this. This would be a more effective design, but the dashed line, the black dashed line is not really following the maximum eccentricity that is possible in each span. So, in that process, what will happen is you will end up putting more pre-stress, which is not otherwise required. So, there is no need for design engineers to choose concordant cable profile. It is a theoretical concept just to understand that it helps in reducing or getting away with the secondary moments, which is not really required in my point of view. Okay. So, for a concordant profile, there is no reaction at any support, there is no possibility of deflections at the supports as well. So, that is another important thing that we need to keep.